learn statistics is like a story. And of course, today the focus is going to be on confidence interval. Okay, but before I go into the confidence interval, I think we need to have a kind of recap. How do we find ourselves doing confidence interval? Of course, going to tell you, going to give you that information about how we find ourselves in a situation where we need to figure out interval estimator. I think the whole story actually started from, trying to or figuring out the true value of a parameter. Of course, before now, I think I've already show you some parameter. Could be mean, could be proportion, could be standard deviation, could be difference of means, could be difference of proportions, and so on like that. I remember before now, I actually unfold, some common unbiased estimators. Of course, you know, the idea behind estimator, I told you the other time, is just like we don't have enough resources to study entire population, because if you want to figure out the values of parameter, you need to study every item in the population. And don't forget, we are limited by budget. And because of that, we're going to take a sample. And when we take a sample, of course, we want to be able to compute the value of the parameter from the sample. When we're doing that, we're not going to get the exact value. I told you the other time, what you're going to end up getting is what I'm going to call an approximate value. And that is not surprising, because whatever estimator, whatever model we use in statistics, we actually want to approximate reality. We are not going to, our model cannot be equal to reality. And because of that, so we're going to have, what we call an estimate. Of course, you use parameter to get a value that we call estimates. And of course, if we investigated, we got some properties of estimator. Of course, I walk you through the other time. If I really want to know how good is my estimator, of course, we can investigate for unbiasedness, efficiency, and so on like that. I think what we focused on the other time was just a point estimator. The point estimator will only give you a single value. And let me tell you this. According to the classical approach in probability, a single value could be wrong or right, even if you have done all the necessary things. I'm going to say that again. It is very dangerous, okay, to actually rely on a single value. A single value is a point estimate, and a point estimate actually comes from point estimator. And therefore, to be on the safer side in research, of course, we needed to incorporate what I call, an error margin. Of course, what we did on Friday, where we place an error bound, a probability bound, okay, on the error. And in the end, you'll be able to see we created what I call a margin of error. With the margin of error, that will enable us to actually rely on the point estimate. If I want to know how reliable is the single value that I got, of course, I need to be able to incorporate the margin of error, where I consider the error to the left and the error to the right. And you know what? And that is the reason why we're into confidence interval. Let me tell you this. There's something that we call point estimator. There's something that we call interval estimator. So the point estimator will give you a single value that could be wrong or right. The chance is 50-50. And to be at the safer side in research, we don't want a situation where we've committed a law to the research, but only to be let down by a poor statistical tool, or only to be let down by, using a point estimate. And that is the reason why we want to consider what we call interval estimator. With the interval estimator, we're actually going to have a way to describe the value of that value in the interval. We are actually going to incorporate what I call the level of confidence with the associated degree of confidence. We can boastfully say, okay, we can authoritatively say that the true value of the parameter will lies in the interval. Okay, of course, in the outline, I've had a review on the point estimator. I'm going to go into interval estimator. But before going into interval estimator, I come across this example online and I love it. Okay. You are preparing for midterm, right? And of course, at times, you can be given a question where they're going to tell you, okay, what is the value of a constant that we make an estimator to be unbiased? Because let me tell you, the ideal situation, what we actually want is for an estimator to be unbiased. I told you the other time, it is not all the time that estimator can be unbiased, okay? But there can be some questions where they're going to tell you, what do we expect the value of a constant? Maybe the estimator is not completely defined, okay? Maybe the estimator actually have a constant in it and they wanted to figure out what would be the value of the constant that will make the estimator to be unbiased. Now, I come across this example using a rod of length. You lay out a square plot whose length of each side is mu. Thus, the area of the plot will be mu squared. Okay, you're talking about square plot, right? All sides, they're going to be equal, right? And the area is going to be mu squared. And maybe the mu squared that's unknown. It's a parameter, right? It's a parameter, it's unknown. Now, based on independent measurement, of course, you're going to have a repeated measurement, right? X1 up to Xn of the length. And the question now is estimating mu squared, okay? Assuming that each S has a mean mu and a variance sigma squared. And the question is asking, show that X bar square is not an unbiased estimator of mu squared. Because why do you think somebody is going to have that kind of suggestion? Because we've already proved that X bar is an unbiased estimator of population mu. And somebody can say, oh, okay, when I square X bar, can that also be an unbiased estimator of a mu squared? And the answer is no. And you're actually going to see why the answer is no. Okay, then in question B, for what value of K is the estimator? X bar squared minus K S squared are unbiased for mu squared. Now, let's get into business. I'm going to show you this. Now, we want to first show that X bar squared is not an unbiased estimator of mu squared. Of course, you know the definition for bias, an estimator is said to be unbiased if the expected value of the estimator can be equal to the true value of the parameter. Now, take a look at this. You know that the variance of X bar, of course, let me first start from variance of X. You know that the variance of S can be equal to the expected value of S squared minus the expected value of S all squared, right? Then similarly, the variance of X bar will be equal to expected value of X bar squared, okay? Which expected value of X bar squared minus the expected value of X bar all squared. And of course, if I want to solve for expected value of X bar squared, that is what I'm going to get. Now, let us now start plugging in, okay? We want to plug in for variance of X bar. You all know that in this class. The variance of x bar is sigma square over n, right? The variance of x is sigma squared. I can use x, I can use y, okay? Don't be confused, okay? Okay, I can use x as a variable, can use y as a variable, can use whatever as a variable. Right now I'm using x, okay? Now, and what is the expected value of x? Mu. Expected value of s is the same thing as expected value of x bar. You know that? Okay? That's going to be mu. Then when I square that, I'm going to have mu squared. Okay? Now, what am I expecting to get? Okay? For x bar squared to be unbiased, I was expecting to get the expected value of x bar squared to be equal to mu squared. But right now, this is biased because what I got is not like that. Okay? What I got is not like that. And that is the reason why if I want to figure out what is my bias now, this is my bias. And that is how, you see the way I calculate that, that is my bias. Now, is this, if you consider S bar squared as an estimator, okay, what is the implication? When an estimator is biased, bias could be a negative, could be a positive. When a bias is positive, it means that estimator will overestimate. When it is negative, it's actually, if you take a look at this, you're going to see that we are adding this to the mu squared. That will lead to overestimation of mu squared. We don't want to, you don't want a situation where we're going to overestimate. We don't want a situation where we're going to underestimate. The two are not good. So this is to tell the world that x bar squared cannot be used as an unbiased estimator for the mu squared. Any question? Okay, now the next question is this. You are given this guy. Okay? Maybe the reason why somebody is proposing that estimator is because using x bar squared as an estimator, we overestimate. And somebody is now trying to subtract something. Okay, subtract, maybe it overestimate that. So subtracting something, you may find yourself around the middle line. But right now, the estimator suggested has a constant k. Okay, now we now want to figure out what would be the value for the k for the whole suggested estimator to be unbiased. Okay, now if you take a look at this guy, when you actually expand that, like taking the expectation of all of that, that's going to give you this. Okay, that is going to give you, don't forget k is a constant, that's why it's coming now. Okay, now you remember the other time, give me 1 second. If you take a look at this guy, right? Okay, this guy is for the expected value of x bar squared, right? You remember? Mu squared plus sigma squared over n. Now, if you take a look at this guy now, oh, what is the expected value of s squared? Sample variance. I showed you last week, sample variance, the one divided by n minus 1. Expected value of s squared would be sigma squared, right? And this guy is this guy. Any question? That also I get k sigma squared. Do you understand that now? Okay, now let me tell you this. A situation where I'm actually expecting, which means I'm going to equate this guy to something. Okay, if I really want to determine the values of k, okay, can somebody tell me, what do you think? What am I going to equate that guy to? There's something I'm going to equate. Okay, take a look at this. I'm going to say this again. What am I expecting, right? For unbiasedness, you know what we actually looking for, right? Okay. Now, that guy will be equated to what? Can somebody tell me? And so for K. Yeah, go ahead. No, 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 not the entire thing. The one that I circled, the one in red. Yeah, that will be zero. Sending me a message for extra credit. Okay. Now, if that equal to zero and you factorize sigma square out, right? Sigma square is going to go away when you divide both sides of the IO by sigma square. When you solve for K, you're actually going to get K to be 1 over N. Any question? Any question? Okay, so that is how that is done. Now, I want to quickly go into this. In lower level statistics, when you are trying to conduct a t-test, of course, we got so many assumptions in using t-test. Maybe you are comparing two means. You are comparing means from two independent population, and they assume that the population variance is unknown but equal. Okay, you know, in that situation, you're going to use pool variance, right? Now, take a look at this guy. When you see a sigma cap square, anytime you see a cap, it's an estimator. That's an estimator of a pool variance. How can we investigate that pool variance as an estimator of variance is an unbiased? Okay, you're going to take the expectation. Okay, you want to take the expectation of that guy. The expectation will actually attract the sample variance of the first population and the sample variance of the second population. And we got an assumption that the sample variance of each population, don't forget, we said they are unknown but equal, right? And on their own, they are unbiased on their own. So there's going to be sigma squared, and that's going to be sigma squared. If you solve that algebraically, that will give you sigma squared. Any question? And that is how we know that a pool variance, estimator, is actually going to be, it's an unbiased, okay, for the population variance. Okay, I want to move to interval estimation now. Let me tell you the idea behind interval estimator. I told you the other time, okay? It is dangerous to just settle for a point estimator, okay? And if we really want to know how to trust or how to rely on the estimator, on a point estimator, then it's better we actually incorporate margin of error. Of course, I walked you through that last week. That I actually called, there's always going to be error of estimation. We place a bound, okay? We got to place a bound. Now, with the interval estimator now, we believe that there's a particular interval that actually contains the true value of parameter. But let me tell you this. Even though we normally go into population once, okay? When you, let me tell you this. When you go into, we always go into population one time. I go into population, I take a sample size of 50. That is all we always do. Based on the sample size of 50, if I use a point estimator and get a single value, there's no way I can validate that, that single value. And what I'm actually going to do, I'm now going to use an approach in statistics that we assume that we've gone into the population several times. And what is that approach? When I have something in an interval, our belief is going to be we've gone into the population 100 times. I'm going to say that again. Repetition, right? that we normally do, right? We're going to assume that we go into population 100 times, and the interval, we can actually compute a probability out of the 100 time. What is the fraction of time the true value will be in the interval, because the true value will not be in the interval with 100%. I mean, will not be in the 100% of the interval. I'm going to give you this example. If somebody asks, how popular is the president of a country is? If you ask me how popular the president of a country is, and if I answer and I say I'm 100% sure that the the proportion or the percentage of those that will favor the president is between 0 and 100, of course that's possible, but that's very, very wide. Or you ask me, you write an exam, I say, oh, professor, can you tell me, what is my grade? And I say, okay, I'm 100% sure your grade is between 0 and 100. What are you going to think about the answer? That is kind of wide. Okay. But you know what? We can never get 100% confidence, whether the true value will be in the interval. Okay. But we have some reasonable level of confidence. So we want our interval, just like the same way that we impose some condition on point estimator, we also want to impose some conditions on interval estimator. And the condition number one, can we guarantee with a high probability that the true value will lie in the interval? That is number one. Number two condition is, can we actually have, can the true value be in the interval, and that interval is going to be narrow? We don't want the wider one. We want the very narrow one. Okay. So, and that is what we're trying to do here. Okay. I want you to see interval estimator as a random interval. It's not just fixed, because the belief is we've actually computed 100 intervals. If I say I'm 90% confident that the parameter will lie in the interval, it means out of 100, the true value of parameter will only lie in the 90 of the intervals. If I say 95, then it means out of 100, it's going to lie in the 95. Does that make sense? Okay. Now, and that's why we call that random interval. Okay. And that can be actually computed from data, the same way we compute the point estimate from data. Now, the other time I said a good estimator should be unbiased, should be efficient, okay, should be consistent. We're still coming to other properties of a good estimator. Also, a good interval estimator. When I talk about interval estimator now, I'm actually going to have the lower value, the upper value, and the property is that the parameter, the true value of the parameter should lies within the two values with very high probability. And not only that, with very high probability, okay, we don't want a wider interval. Just like the one I gave you the other time that I said, okay, your score is going to be between 0. I'm 100% sure it's going to be between 0 and 100. Oh my God, that is too wide. So we need a narrow one. Okay. Now, because of that, we're actually going to construct a confidence interval. You've heard about that before. In the confidence interval, you're actually going to have what I call interval estimator. Okay. Now, we have the upper limit and we have the lower limit. Okay, the theta cap N is the lower limit. The theta cap U is the upper limit. And let me tell you, I know most of the time this is common, two-sided, where you consider error to the left and the error to the right. Okay, two-sided. And we could also have one-sided. Okay, we could also have one-sided of the interval. Okay, This is for the upper one, and this for the lower one. Okay. And the probability, okay, that the random interval will contain the true value of the parameter is actually called, the confidence coefficient. Okay. Don't forget, why do I need to figure out the probability? Because we want a situation, we want to see whether are we going to have high value for probability or not. What are we anticipating? We're anticipating for high value. We want the parameter, the true value of the parameter, to be in the interval with a high probability value. And that is why we normally use high level of confidence. Okay, that's why we use high level of confidence. Okay, now for the two-sided, this is it. Where the true parameter doesn't have a curve. That's a true value of a parameter. Line between the lower limit and the upper limit. Why is it that the lower limit has a curve? Because don't forget, it's going to look as if we are constructing 100 intervals. Oh my God, there will be 100 form of the lower limit. So the lower limit and the upper limit varies. They are random variable. That's why you see a cap on them. But the parameter theta, okay, is fixed, is unknown value. Does that make sense? Now, and I told you about one-sided. Right? If I want to figure out one-sided, right? Okay, this is for one-sided. This is another one. We got two type of one-sided. Okay. Now, I'm going to go into example now. Let's take a look at this. Suppose that we obtain a single observation y from an exponential distribution with mean theta. Okay, use y to form a confidence interval for theta, okay, with a confidence coefficient is 0.9. Now, some of you may want to know the difference between confidence coefficient and the level of significance. The level of significance is alpha, right? The maximum probability of committing type 1 error. The level of significance and the level of confidence are mutually exclusive. If the level of confidence is 90%, then the level of significance will be 10%. Does that make sense? Okay, just wanted to take the note of that. Now, here, suppose we obtain a single observation y from an exponential distribution. You know the probability distribution. Okay, the mean is unknown. The mean is theta is unknown. And you now want to use information that you got on y to form a confidence interval for theta with the confidence coefficient. Let me tell you, anytime you want to construct a confidence interval, you need to be able to disclose your level of confidence. Okay, now suppose that the confidence level is of the form, okay, don't forget the random variable is y, right? And where a is less than b, you know, b is bigger, right? Take a look at this. If I have y, I'm just assuming over 10 and y over 5. Okay, which one has a bigger denominator? The one with 10. The one that have a bigger denominator will be smaller. That's why you see y over b at the other part and y over a at the other part. Okay. Now, and a constant that do not depend on theta. Of course, they shouldn't depend on theta. Don't forget, we want to figure out the true value of theta. Therefore, they shouldn't depend on theta. Now, we want to find the values of a and b. Okay. Now, if you want to find the values of a and b, then you actually want to find the probability that the parameter will lies between that will be equal to 0.9. Where is the 0.9 coming from? That is your anticipated level of confidence. if you are seeking, mathematician will say, when you describe a value in an interval, there's going to be error. Okay, there will be error. Anytime you describe anything in an interval, there will be error. I just wanted to take note of that. But in statistics, and that is why we want to come with a confidence. Oh, 90%. What is the probability? That is 0.9. That's 90%. Now, if you take a look at this, mathematically speaking, I can rewrite that as this. I can rewrite it as that, which means I will just go to the distribution. I'm working with a probability density function. Exponential is a continuous probability distribution. If I want to seek to get the probability of the value lies in the interval when I'm working with a continuous probability distribution, then I must be ready to perform an antiderivative on the PDF. And that's exactly what I'm doing here. I want to perform an antiderivative on the PDF. Y is a continuous random variable coming from, exponential distribution is one of the continuous random variable. Now, A theta to B theta, of course, what is my f of y? I'm plugging that guy here now. When I solve for that, and I plug in that, I'm actually going to get this. Any question about getting exponential raised to power negative A minus exponential raised to power negative B? And of course, if you really want to see the graphical, representation of that, okay, now you can see that. Now, we're now going to make certain assumption. When you take a look at that graphical, if you look at the graphical expression, you're actually going to see the red line, right? 0.9, right? 0.9 actually fall between the 0.05 and 0.95. I can actually say, okay, let me call this one part. If this minus this actually give me 0.9, I can think of two numbers that will make sense. If you look at the graph, then I can say 0.95 and is minus is 0.05. Is 0.95 minus 0.05 is that, then I can actually let that guy to be equal to this and this guy to be equal to that. Okay, I can let that equal to that and that equal to that. Then I can actually take the log of both sides to obtain the values of A and B. And of course, when you do that, you actually going to find yourself right here. The values of A and B can be determined to be that. Okay, A is 0.0513 and B 2.996. Okay, so take a look at that. And after that, then I can now tell the world that we are 90% confident, okay, that, the true values of the parameter theta will lie between that guy. You now plug in the values of, don't forget, let me take you back to where we start, this is, can you see that, right? Can you see that guy? Just plugging in back your B and plugging in back your A, okay? And that is how we got that. But we got a lot of questions here that need to be answered, okay? Now, take a look at the first question. Suppose that in a realized experiment, Y is observed to be 1, right? Can we conclude that the probability of theta being between that is 90%? Okay, we can never conclude that, because don't forget, the idea of 90% is trying to tell you that out of 100 intervals, okay, the true value will only lies in the 90. It is not going to lie in the 10 intervals. So when I'm considering Y to be is to be 1, which is maybe one of that, okay, there's possible. I don't guarantee that. Does that make sense? That is not guaranteed at all. And that was why we said no. Okay. The theta is a fixed constant. I told you, theta is not subject to variation. What is subject to variation is your interval estimator. The location of the interval, subject to variation. It's random. But the theta, the true value, doesn't change, even though it's unknown. It's fixed. Okay. And that was why I said it is not, okay. So I said theta is fixed constant. Thus, either theta is within or that is actually going to be 0 or 1. It could be there or not. And anytime you see me zero, well, I'm using 0 or 1, that's too dicey. That is dicey. That is more or less like a point estimator. A point, that's more or less. And that was why I told you the other time. A point estimator could be right or wrong according to the classical approach. It could be wrong or right. That's 50-50. Okay. And that was why we said this. The probability. Don't forget, we plug in y to be equal to 1. Okay. It could be either there or not. That's what we mean. And take a look at this. But we could simply say a observed 90% confidence interval for theta is that observed. We could simply say that. So we are 90% confident that that's enclosed theta. When I say we are 90% confident that that's enclosed theta, that is what we could simply say. Now, and I put this, I said the confidence coefficient identify the fraction of the time in repeated sampling that the interval constructed will contain the target parameter theta. If I say 95%, which means I'm confident out of 100 intervals, it's only 95 that will contain the true value. Okay, what about the other 5%? Oh, the other 5% is a level of significance, which is a level of statistical error, which is the numbers of time we can mislead the audience, the populace out of 100. Excuse me. Now, if we know that the confidence coefficient associated with our estimator is high, we can highly be confident that any confidence constructed by using the result from a single sample we enclose. See that? Don't forget, we go into population once. But the idea of the interval, will enable us to know how reliable is our point estimate. We'll be able to know how the sample that we've chosen from population reflect the overall view of the population. I'm going to go into another example now. Suppose that we take a sample size of n equal to 1 from a uniform distribution. This is another distribution now. Defined on the interval 0 theta, where theta is unknown. Find a 95% lower confidence bound. I told you the other time, we have a lower confidence bound, upper confidence bound, and the two-sided. Now, take a look at that. Suppose the CF is this is this. We're talking about the lower confidence bound. So y over a, okay, comma infinity. You remember what I showed you the other time, which means I may need to figure out the values of a. Okay, and therefore for y is 1 over theta, and this time around the probability is actually going to be equal to that 0.95, y 0.95, 95%, 0.95. The other time we were seeking two-sided, and that was why we computed a and b constant. But right now it's only one-sided. That's why we're looking for a. There will be another one where you're going to be looking for b when you're looking at the upper bound. Any question? Okay, now if you look at the left hand side, okay, if I have y divided by that, if I can multiply both sides here by a, which is just going to be that, right? Which is going to be this guy, right? And we can impose 1 if A theta greater than theta, like if A greater than 1, we can impose that condition. And I needed to take a look at this, just like what we do the other time, where we're looking for, we have a 90, and of course we believe that will be the difference between 0.95 and 0.05, but this time around, is take a look at that guy. Now, from there, you're actually going to see that the only reasonable value, the A, can actually be in that scenario where A is greater than 1 is to be 0.95. And of course, if that would be the case, I'm actually going to have this as my conclusion, where I'm going to say, since I've already determined my A, okay, is that it's a 95% confidence interval for theta, okay? But I'm going to say I have to specify lower confidence bound for theta, okay? With 95% confidence, theta is larger than that. So I needed to take a look at what I have. Now, to demonstrate that we have 100% interval, because so many interval, take a look at that. Here now, I'm trying to show you 24 intervals. If the true value is 0.5, right? Do you see true value here? If the true value is 0.5, okay, what we have plotted here is like the estimated, when you take a look at what you see here, the estimated probability value, and you're actually going to see, if you count all this guy here, they're going to be like 24 of them. Okay, it is not going to be all of them that will contain the true value is 0.5 that we talk about. It's not all of them. Okay, so that is what I'm just trying to let you know. Now, in this summary, if the same procedure was used many times, I want you to take a look at that. The same procedure was used many times. What make why do we call an experiment random? Okay, a random experiment is an experiment that you perform repeatedly under similar condition, but you know what, they give different results. Okay, now if the same procedure, you use the same procedure many times, each individual interval will either contain or fail to contain the true value. Does that make sense? Okay, but the percentage of all intervals that capture P will be very close to 95%. And this is one of the reasons why it is very common to use a level of significance 5%. That doesn't mean we don't use other level of significance. When the level of significance is 5%, then it means 95% level of confidence. Okay, now you are 95% confident that the interval contains the parameter because the interval was obtained by using a procedure that generates interval that do contain parameter approximately 95% of time. So if I'm 90% confident, it means out of the 100% of time, that is, I'm going to view that as 100 intervals, then it is only 90 of the intervals that will contain the true value of the parameter. Is there any question? There's going to be an in-person lecture on Wednesday, but on Friday, like I said, we're going to have a virtual lecture where you're going to log on to the Zoom. And this week, I think tomorrow, I'm going to release midterm 1 practice questions. And okay, go ahead. Oh, when I'm releasing homework today, right? Oh, you mean homework? Releasing what? You mean, oh, you mean I've released homework for? My bad. I save it and I forgot. You know what I'm going to do? I'm sorry about that. it will be extended. The deadline for submission of the homework 4 will be extended by 48 hours. I'll post it immediately I get to my office. I save it, but I did not publish it. Sorry about that. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.